For the next one, we're supposed to show that log or the a to the log to the base n of b is equal b to the log base n of a. And then we'll start that. That's such a blanket statement. The thing is, alright. I mean, there are quite a few things we could go into, and I'm not sure if I have time to go into all of them. But, alright, there are some simple log rules that we admit from the start. Things like log of a to the x is equal to x log a. Remember that? Good. And that's actually the only principle that we're going to use to solve that one. So if you understand that part, we know that we can actually multiply, well, take logs of both sides. If we take the log to the base n of both sides, we end up with n of a to the log base n of b is equal to log base n of b to the log a. Don't let the functions confuse. It's just another function there. Now, since we know that log of a to the x is the same as x log a, we can then simplify this by moving the exponent to a multiplier here. So, with that simplifying both sides, we end up with log base n of b times log to base n of a is equal to log base n of a times log to base n of b. So that's a proof. The reason log scale is so important is that it allows us to handle really big numbers in a compressed space. It's a function that compresses, you can say, it compresses large numbers. So when you're dealing with analysis of algorithms where you may be looking at functions that may change and the order of the you need to manage the change depending on whether it's working on 10 items, 100 items, 1,000 items, a million items, a billion items. So that may be the scale in which you need to give your reports on. So sometimes you may be looking at a graph on a log scale. Sometimes the behavior of a function changes relative to the log of the number entered, right? Now, there are times when the behavior changes relative to the actual number of times, number of things that are being worked on. For example, if I have a function that needs to look at each thing in turn, then every single thing I add to the data set will cause the function to grow according to the number of things I put into the data set. Now, if I could get a more efficient way of working with it, of looking through that data set, for example, splitting the list into halves, and then once I split the list into half, then I just go to another section and work on a half, and then split the list into halves, and I'd be working with not a linear behavior, but rather a different type of behavior. So that's why it's useful to introduce the log function. I may not need to know all about it as much as a mathematician would need to know, but it really helps us in analyzing. So a little bit more background work is always useful if you think you kind of weak in this area.